Welcome, everyone. My name is Daniel Bayer. I'm an application engineer at Cadence, and I'm your host for this session. The title of the session is Create Palladium Design Equivalent to both Specification and Gate Implementation on Silicon. And the speaker is Sathappan Palaniappan from Broadcom. If you have any questions during the presentation, please type them into the Q&A box in your control panel. We'll bring them up at the end of the presentation during Q&A. And now a few words about the speaker. Sathappan works for ASIC product division of Broadcom. His expertise lies in front-end design, ranging from architecture, design, RTL coding, synthesis, formal equivalence verification, STA, DFT, and so on. He has 5 published patents. And now over to Sathappan.
Hello CDN Live audience. I am Sathappan Palaniappan. As a part of ASIC product division in Broadcom, recently we created a Palladium model for one of our complex IP for Palladium Z1 platform. I am going to share some of the experience in today's presentation titled Create Palladium Design Equivalent to both Specification and Gate Implementation on Silicon. Broadcom. I come from ASIC product division of Broadcom. Nature of our business is to receive customer synthesis netlist and deliver them extreme quality fabricated silicons. Not limiting to it, we also have industry's outstanding advanced IPs which get along with the customer IPs. In the presentation, I'm going to give a short introduction about starting Palladium Z1 flow from RTL and from gate netlist, about Palladium Z1 in ASIC flow, compare the results of RTL Palladium Z1 flow versus gate netlist Palladium Z1 flow, conclude with what worked better for us so that you will have some takeaway from this presentation. Artificial intelligence hardware consists of array of processing elements, basically repeated IP blocks. Entire hardware cannot fit into a single chip, thus SerDes integrates the chips. Simulation at top level takes huge compute resource and wall clock time. Sometimes it is not possible to simulate such a large design when they are connected by SerDes and if it is multiple chips that's getting integrated together. However, the simulation acceleration and emulation in a single environment is possible using Cadence Palladium Enterprise Emulation Platform Emulator and Verification Xccelerator Emulator software called VXE software. So basically, any spec intent is captured in the form of IP. So this IP can be either an RTL or a firm macro or a hard macro. So in an AI chip, either a single processing element or cluster of a few processing element form a hard macro, or even the SerDes form the hard macro. So these things are forms a single chip, in fact, or single hard macro if it is an IP. So it can be even a single chip. Later, multiple chips will be connected by SerDes, and this whole thing as a system will be dropped into the Palladium, right? So the goal here is whatever we are planning or aiming to targeting to drop it into the silicon, if we can drop it into the Palladium as is. Basically, when I say as is, not even touching a single line of the netlist file, if we can drop it as is, that is what is the objective or aim of this presentation. So the silicon that is targeted for the netlist that is targeted for silicon is what targeted for Palladium emulator also. So key for simulation acceleration or to be very precise, key for Palladium performance is clock modeling and clock generation and division. So this presentation describes how to create Verilog hardware IP for Palladium Z1 emulator close to both specification and the gate level implementation on the silicon using VXC design verification system. So I've just taken an IP right from RTL, taken through the Palladium flow, taken the same IP starting from gate level netlist, taken through the Palladium flow. So in the end, I'll be comparing both the results and then put with what worked better for us. So here are the early stages of ASIC flow. Basically, the design intent is captured as a HDL in design interface. It is verified during pre-layout simulation and declared golden. The golden RTL is synthesized and output netlist equivalence is formally compared against the golden RTL. So in case Palladium flow is started from RTL, during logic synthesis phase, you import and synthesize HDL design using VA VHDL or VA VLOG and elaborate using VA ELAB. On the other hand, if you want to start the Palladium from gate netlist, during logic synthesis phase, you read and synthesis HDL design targeting standard cell library. Basically, this is your regular logic synthesis wherein synthesis netlist is later dropped into silicon. Thus, both the netlists are not one and the same. They are apples to oranges and not apples to apples. One of our complex IP design, let me say a synthesis netlist, consists of analog block, digital block, and clocks block. As the analog blocks are mixed signal components, they are not directly portable to Palladium emulator. Hence, basic feature of the analog blocks are modeled using HDL language like System Verilog. A black box cake divided module is instantiated as a placeholder. Later, during clock modeling, decomposed clocks are dropped into it. This RTL is synthesized as a standalone block and added to the top gate netlist after trashing the corresponding embedded timing model. As we started from synthesis gate netlist, digital blocks are kept as is. However, if there are memory macros, they are mapped to Palladium using Xcompile. Similarly, all the standard cells are mapped to Palladium using Xcompile. As a part of clock generation and division, Palladium's F clock is mapped to highest frequency clock of the design asses. In that case, we use Palladium's cake 1x technology. Otherwise, if Palladium's F clock is divided by 2 and then mapped to highest frequency clock of the design, then we use Palladium cake 2x technology. All other clocks are further decomposed from design's highest clock. The divided clocks are ported to the cake divided module in analog block. So now, when we start from gate netlist, let us see what were dropped into the Palladium emulator. Clock blocks contain two things: clock generation, basically mapping of design's highest frequency clock to the Palladium's F clock, and the second part is clock divided or cake divider. Analog block contain two things. One is system Verilog model of the analog block synthesized to a gate level netlist. The second part is the cake divided black box module with number of outputs equal to the divided clocks of the design. So basically your design has various clocks. The total number of clocks should be equal to the number of outputs of the cake divider module. So we will be creating the clocks on the output ports of these modules. So digital block again contains two things: the technology dependent standard cells and other hard macros. For example, these hard macros can be a memory macro or any other hard macro of your chip. Right. So one special thing here is Instead of mapping the standard cell in the gate level netlist to a Q cell or a Palladium cell, the standard cell Verilog library package itself is mapped using Xcompile. Indeed, this is one-time process and can be used for all other IPs even. So basically what I mean here is, so let's say there is a AND gate with a 2-input AND gate. So the AND gate head or the module will be matching your standard cell cell name, whereas its body or the content will be your Q cell or Palladium cell. So like this, you just create a wrapper for each and every standard cell that is there in your technology library with Palladium cell or Q cell in it. So this can be done using your Xe compiler for your entire library package. So it could be your TSMC standard cell library package, and you can just directly convert all the library packages to a wrapper, something like this. And this can be used across project to project or across IP to IP. You can reuse this. So this is kind of a one-time process. So you just, if you're let's say if you're in a 7nm technology or 5nm technology, the technology library cell, you just blindly convert and then keep it ready for you to use it in your Palladium flow. So later, the gate level netlist is compiled using VLAN compiler with respect to the above converted library package. So as we saw earlier, the memory macros are also mapped to the Palladium cell using Xcompile. So now this entire digital part of your design plus your analog part of your design, along with the actual cake division or a clock division will get into the block box area and it will get filled. And this forms your DUT top, and your clock generation part forms. So now together you can just, since it's an IP level, you can just do your basic verification using a test bench, and that will be your test bench top. So the DUT top and your clock stop will get into your Palladium Z1 emulator, and your TV top will get into your host. So in case if you are writing a synthesizable, or in other words, a Palladium compatible test bench, even the test bench can be dropped into emulator to get your utmost performance. Since the test case what I have taken is at IP level, my test bench, we have kept it on the host. So the test bench was not dropped into the Palladium emulator. So basically, I can reuse a test bench that was used at the simulator, since it is IP level. And this simulator, this test bench need not to be a synthesizer, need not to contain all Palladium compactable constructs, since it's running on the host. Right. So having said that, now the design got into the emulator and the test bench is sitting in the host. Let's see how the Palladium flows using the scripts required, or what are the steps required to get this till the stage of running the emulator. Right. The first step involves utility is used to choose the cake technology and map the Palladium's F clock. So the test bench which will be there in host is compiled separately using a VLAN TB. And the design synthesis netlist are compiled using VLAN net. So basically, if you see, there is a switch called dash netlist. So underneath, whatever you are listing out should be all in the form of netlist. So basically, when I say in the form of netlist, even sometimes you may create a hand instantiated netlist, and those things should be as if it is a tool written out netlist. So we will see the advantages of this during the conclusions when you use all netlist. So the next step is compiling your clock. So IX clockgen produces a clocks module out of the cake divider information that you have provided. So the clocks module is compiled separately using a VLAN clock.quip. The cake divider information is there in a file called cakeclockdivider.sv. So basically, this will contain your source clock. So basically, the highest frequency clock of the design is mapped to your Palladium's clock. So here I am just calling it as a PF clock. To that wire, you just map your highest frequency clock. And using that clock, you get the other subsequent clocks or division version of the clocks of your design. So you tell your source clock and then what is the output clock with their respective ratios. And this particular thing, I'm just preparing the cake file so that this can be quickly switched between cake 2x technology and 1x technology. So always it is better to start with cake 2x technology and then later move to the cake 1x technology. So now, not only this, like if you have any assertions or something, again, you can have a separate VLAN, or you can just have the VLAN assertions along with your VLAN clock. So even for adding assertions, you will follow same technology, same technique, wherein you create a black box for your assertions and then get this black box synthesized along with your analog block or something. And then later you can go and fill in this black box using your assertions. And then that assertion file can be again compiled using a separate VLAN. So now all that of your VLAN steps got over. And then now it's time to go and elaborate your design. So for which you'll be having a script called ixcom.quil, wherein you will just tell what is your compiler options, like how much resource of your Palladium boards are required for you to compile, and what is your tops. For example, in our case here, the test bench becomes the design top, and then your gen clocks becomes your another design top, right? So in case if you are dropping your test bench into the Palladium box, even that will become your design top. Or in other words, like if you are targeting at the chip level and you don't have any test bench, you are only going to wiggle your resets from the chip level. In that case, your design top will become, your DUT will become the design top. And then you will have a clock generation top. Right, so this is the compiler options.quil, wherein you just go and tell how much board you required, what are the other compiler options that you want to have. And all those compiler options are added to this particular file. And this is net2step.spec, wherein all the VLAN compiled and elaborated stuff now is available in a folder called work. And when ixcom is called, ixcom will go and then look for the netlist inside this work folder. And from that thing, it will try to resolve all other things looking at or fishing from the work folder. So the default is capital work folder. So in case if you want to do a mix and match compile with RTL and netlist, you need to have the RTL compilation in a separate work folder, which will be named by the user. And you will just go and tell your nlreflib to your user named work folder. And any default netlist compiled using -netlist option will be kept in default work folder called capital work. Now, in the nlreflib, if you tell your user work folder along with your default work folder, ixcom will go and look for the netlist and other modules connected to the netlist and try to elaborate the design. And what this NL hot swap option is, like whenever you are just compiling your design, it will just compile it for the hardware itself, and also it will create, and basically it is called as a hardware model, and also it will create a software model. Now, if you want to switch between the hardware model and software model, you will have an option to switch. So if you want to enable such a software model, you just go and enable this NL hot swap on. So default is off. What it means is it will just create only hardware model, and you can only run your emulator or run your emulation in the hardware. Whereas if you have even the software model, you can run your emulation both on the software model and also on the hardware model. So depending upon your logistic requirements. So now you have got your compiled database plus the emulated database. It's time to go and then emulate it or run your emulation. So your emulation is run using a utility called Xcdebug, and this is how you run the script. And the run palladium.tickle is something, a simple tickle looks something like this. You just basically connect your debugger to your current folder, wherein your work folder or your project workspaces, and you connect your host also to your current work folder. And then what the next command does is to go and then initialize all your x's to zeros and tri-states to zeros, and you go and reserve trace mem size for having a glimpse of the waveform, so that it will just give you a snapshot of your waveform. In case if you want the entire waveform to be dumped, which is a very time consuming task, which you may be bounded to do when you have some bugs or when you want to debug, you just increase this trace mem size so that you can capture the entire waveform. And you just run your design by, you can also probe your designs, various points of your designs, and then you can just upload, and then so that you can keep your waveform database very simple and then affordable or could fit into your reserved trace mem size. Once all those probing is done, you go ahead and run it. Once the emulation is fully run, you just go and then upload the database so that you can view the waveform in the waveform viewer and then do your debug. So this is how you run your Palladium. Now, so here are the results from my RTL sim flow, RTL emulation flow, and gate emulation flow. The simulation and emulation are at IP level. The test case is very simple, just to sanitize the IP at block level. So the compile and elaboration time chart results are not exciting here. However, still we can have some inference out of it. For RTL or gate simulation, before running the simulation, you need to compile and elaborate first. The compile and elaboration time, similarly for RTL or gate emulation, before emulation, you need to compile and elaborate first. The compile and elaborate time is what is given here, right? So RTL simulation took somewhere around 1 minute, whereas a gate simulation took around 8 minutes. Whereas when the same RTL compiled for emulator took around 5 minutes, when the gate level netlist compiled and elaborated for emulator took around 3 minutes. So what you see on the right hand side is the gate count. When I compiled the RTL, the reduction I got is closely 49% of reduction. Whereas when I try to compile the gate level netlist, the reduction what I got around is 44% of reduction. So the point to note here is gate level netlist is already optimized by your RC compiler or any logic synthesizer. So what has happened on top of it is Palladium is again optimizing it. So this optimization could be like if you have any dead cells in your design. So for example, if you have got your DFT logic and you have got your tie constants due to that, and if the constant is getting propagated, so those dead cells will get eliminated or removed, which is not required for the functional simulation. Similarly, even in the functional simulation, let's say in your actual silicon, you have a 2 memory macros, and if Palladium simulator understands the address bus to the memory macros that's going to 2 memory macros or same, it will just merge the memory macro and then map it to the Palladium's internal memory resource. So thereby it again optimizes. So these are the major areas wherein Palladium optimizes. So how it helps is when you have a larger design and a limited resource of the Palladium box, because we are trying to put the entire system here, not a single chip, right? It's a multiple chip connected by SerDes chips. We are just trying to put the entire system into the emulator, right? So always you will have a fight to fit your design into the emulator box, right? So you need to compress it, you need to optimize it as much as possible so that you can fit your design. So that's very much possible when you re-optimize the gate level netlist. So here, for obvious reasons, like I didn't go and had the test tie-offs, so hence I didn't see a drastic gate count reduction because one of our objective was to drop the netlist as is, not even touching a single line or not even adding any constraints to the netlist, so that we want to see whatever getting into the silicon, we want to get the same thing into the Palladium emulator. So since that being the objective, we didn't give any further constraints so that the gate optimization also will look like RTL optimization. So in this case, the gate netlist contains the extra DFT logic and the gate do not have the DFT logic. So here is a comparison of the emulation speed. So this is the runtime speed. So when I compare the RTL simulation versus the RTL emulation, it was around 25x times faster, whereas gate simulation and gate emulator was 633 times faster. But this is a very, very simple test case which runs in few seconds. So if you really have a larger test case which runs for a days together in the simulator, in emulator, you can see up to a speed of 10,000x. And here are the critical path and emulation speed of my design when I targeted the RTL and gate level netlist. So RTL had 208 steps. So each step is equal to 1 unit delay, and that's how it's measured. And gate had just 180 unit steps. So similarly, your emulation speed is inverse of your critical path, right? So RTL I can go up to 2387 kilohertz, whereas gate level I could go even more above 2743 kilohertz. So that brings to the conclusion. So basically, getting developed early. However, my recommendation is as soon as you have the gate level netlist ready, start the Palladium flow from gate level netlist instead of RTL. So it enables early software development and post silicon debug as well. You no need to wait for your silicon to come. Rather, you can start your software development after dropping your design into the Palladium emulator. So the gate level netlist is used as is, treating standard cell libraries as wrapper around the Palladium cell. And so since we are not touching even a single line of the gate level netlist, there are no two gate level netlist. It's a single netlist file which is getting dropped into the silicon. Also the same netlist is getting dropped into the Palladium. Hence, there is no need of FEV. Otherwise, formal equivalence verification, you need to do it between netlist to netlist, and that will have its own complexity and issues, which you need to deal with or debug with. Right. Another good thing is like if you start from the gate level netlist, it's a simple and quick gate netlist compilation and elaboration. The reason for that is the gate netlist is written out basically by a tool. So it could be your RC tool writing out your netlist, or your implementation tool writing out your netlist. So since the tool is writing out a netlist, obviously you won't find any syntax error, or everything is Palladium compatible. Constructs will be there in it, and then it is easy to compile. So it doesn't vary person to person. So no need to deal with few Palladium supported and synthesis non-supported system Verilog constructs like behavioral code. For example, initial blocks or sharp delays are supported in Palladium, but it is not supported in synthesis. So you don't need to bother about all those things. So gate level simulation is slower, whereas gate level emulation is typically 10,000 times faster for any larger designs. Thank you. So that brings to the conclusion of the presentation.
Thank you, Sathappan, for your presentation. We unfortunately ran over time, and we do not have any more time for Q&A session. So Sathappan will answer to your questions per email after the show. Thank you for attending.